Hi there, so here's the second part of electron arrangement. We're dealing with the full electron arrangement, dealing with S, P, D, and F. You'll need your periodic table for this, and if you also have the small periodic tables, label that and put that into your notes as well. If you don't have it, just come see me later on. We're talking about the electron configuration and exceptions to it. So we know that the simple electron configuration is found in the lower left-hand corner of your reference tables. And they tell you which energy levels there are and how many energy levels there are and which electrons are in there. So for example, like this first one, hydrogen, it has one energy level because it's in period 1, and it only has one balanced electron. Same thing with lithium. It's in period 2, so there's 2 different levels, and the last one only has one balanced electron. 3, there's 3 different levels. 4 different levels. So that's the simple electron configuration. There's also a full version. I want you guys to see this one as well, because it explains why there's different why there's different oxidation numbers. So with this one, we actually have 3 different parts to this. We have the principal quantum number. It sounds so fancy, but it's pretty much which period it's in. All right, so it means the distance from the nucleus, but it also means which level it is. So for example, with lithium, this is period 2, so it would start out with 2. It also has sublevels. Label this in your reference table. Sublevel S is groups 1 and 2. Sublevel P are groups 13 to 18. The D are the transition metals, and the F are going to be the lanthanides and actinides. If you need help remembering S, P, D, and F, well, my name is Sanel Patel Dame, and we can add Flynn in there as well, or electrons are my friends. So I kind of do enjoy teaching this part because my initials are right there. Then we have the number of electrons, and those are a superscript. So let me show you pretty much what those S, P, D, and F mean. We say that electrons are in the orbitals. Well, these are the orbitals. We usually show the Bohr model showing the nucleus in the middle, and then we have electrons on distinct energy levels outside of it. I mean, this is easier for us to draw, sure, but really electrons are in orbitals. So these are what the orbitals mean. The S is actually going to be a sphere. The P's are going to be dumbbells going along the X, Y, and Z axis, so there's 3 different types of P's. D's are going to look like flowers, I guess, like they sort of look like flowers, and then there's 5 different types of those. And then F's are, I mean, I can't even describe these guys. So they seem very difficult. You never need to memorize this, but I want you to visualize. Those electrons aren't in distinct orbits around the nucleus. They're in orbitals, meaning that they're going to be all around these different levels. So they'll be rotating along or actually located in all these different sublevels. So let's make sure that when we label our periodic table on our notes that we can just show this part of it. The S block are going to be groups 1 and 2. Helium is also going to be part of that S block, so make sure you see that little part in there. The P block are going to be groups 13 through 18. The D are going to be the transition elements, and the F are going to be the lanthanides and actinides. Now remember how I told you that there's only one type of S? Well, these are the S's, that's that sphere, and there's 3 different types of P's. Well, if you take a look, there's actually 6 groups, and there's going to be with those 3 different types, you can have, kind of help yourself remember, 3 times 2 gives you 6. Same thing over here, there's 5 different types of D's, so 5 times 2 gives you 10. There's 10 groups in those transition elements. And then over here for the F, there's 7 different types of F, so there's actually 14 groups in each of these. It's a more advanced, or that's kind of a little bit more advanced than what you need to know right now, but I just wanted to share that with you in case you need to know that for the future for any reason. So if you take a look here, we have 1s are going to be the hydrogen and helium over here. We've got 2s, 2p, 3s, 3p, 4s. Then it goes to 3d, so it kind of goes back up a level, then back to 4p, 5s, 4d, 5p, and then 6s. Don't forget that we have those lanthanides and actinides, so it goes to 4f, then 5d, 6p, 7s, down over here to 5f, and 6d, and so on. It sounds really complicated, but it's actually quite easy. I'll show you guys here. So these are all of those numbers filled in. The first number means that pretty much what energy level it's in. The second thing is the letter, the S, P, D, or F. And the third part is the subscript, which is the number of electrons. So for example, hydrogen, we would just call it 1s1 because it only has, it's in the first energy level, it's an S sublevel, and it only has one electron. So let's go through some of these. Let's say, for example, we do nitrogen, which is located right over here. So I'm going to do the energy levels for nitrogen. So I'm going to start all the way at the beginning, as if the periodic table were like a game board, all right? So hydrogen and helium, I can go 1s1 and then over to 1s2. So really it fills up 1s2. Then this is 2s. There's 2 elements in there, so actually there's 2 electrons in there. And then come on over here. This is still part of the 2p's, so it's 2p, but we go 1, 2, 3. So that's 2p3. So if we want nitrogen, it's 1s2, 2s2, 2p3. If I wanted to have chlorine, for example, I'd start all the way at the beginning. So hydrogen and helium makes up 1s2. Lithium and beryllium is 2s2. Then we go all the way over here. That's 2p6. There's 6 elements in there. Then over here, there's 3s2, and then 3p1, 2, 3, 4, and 5. So this ends up being 3p5. So this is what the full electron configuration is for chlorine. We can also do a shorthand notation. So the shorthand notation means that we go from the last noble gas that was located there. So if I wanted to go back, I'd go to neon. So neon would be 1s2, 2s2, 2p6. So really what I can do is just say neon and then go from here. So then I have 3s2, 3p5. So this is the shorthand notation for the electron configuration. So let's do some more. We have, let's see, iron. Let's go to iron. We have 1s2, and this is 2s2, 2p6. This is 3s2, 3p6, 4s2, and then don't forget, when you go back to D, the D's actually start at 3. So this is 3D, 1, 2, 3, 4, 5, 6. So this is 3D6. If I wanted to use the shorthand notation, I'd actually go back to the last noble gas from iron. So go backwards, and argon happens to be that last noble gas. So really, all of these represent argon. And then I continue on, 4s2, 3d6. All right, so those were some examples. Actually, let me give you one more just to make sure we're all set to go. Let's see, let's do silver. Okay, I know it seems like it's really far down there, but the more we do this, the better it is. So 1s2, 2s2, 2p6, and again, that number means 1, 2, 3, 4, 5, 6. Then 3s2, 3p6, 4s2, 3d10, then go back to 4p6, 5s2, and then 4. So 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this ends up being 4d9. If we're going to do the shorthand notation, we go back from Kr, and so this would end up being Kr. And actually, if we take a look, all of these are part of Kr. So these are the only parts that are going to be unique just for the silver. So 5s2 and 4d9. So that's how you do silver. Now, let's look at some of the exceptions to the rule. We have copper and chromium. Copper we expect to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then 3d9. This actually is incorrect. What ends up happening is that the S actually ends up having less energy than the D. So this actually goes right over there. Or actually, we'll show this way. This would be 2, this would be 9. However, the real way to write this is it ends up being 4s1, 3d10. That's just one of the weird exceptions. Same thing with chromium. We'd expect it to be 1s2, 2s2, 2p6, 3s2, 3p6. Then here, 4d, well, actually I'd write this over there, 4s2, 3d4, but actually it ends up that one electron from the s goes over to the d instead, so it ends up being d5, 4s1. Alright, so principal energy levels, it tells you how far away the electrons are from the nucleus. If it's one of the main group elements, meaning groups 1, 2, or then 13 over to 18, you can just go ahead and use the period number. When it gets to the D's and F's, it goes a little bit weirder. D's, you have to start at 3, F's, you start at 4. The sublevels, so groups 1 and 2 are the S block, including helium. Make sure you write helium in there as well. 13 to 18 are the P blocks. The transition elements are the D blocks, and the lanthanides or actinides are going to be the F block. And then the superscript is going to be just the number of electrons. We'll practice this a lot. You'll be great at it. You will absolutely love this. I promise you, kiddos. Have a good day.